Previously, we've talked about how to draw Lewis structures, which show us how the different atoms are bonded together in a molecule. In this video, we're going to talk about Vsepr, which is a way of determining how the atoms in a molecule are arranged in three-dimensional space. Vsepr is an acronym that stands for Valence Shell Electron Pair Repulsion Theory, which you certainly do not need to memorize. We just call it Vsepr. The idea is that when you have electrons in a compound with each other, they want to be as far away from each other as they can because of electron-electron repulsion. They have the same charge, and so they repel each other. What we do is we put electrons into groups, and an electron group can either be a bond or a series of bonds, lone pair, or rarely a single electron if you happen to have what we call a free radical. The general idea is that the first thing you do when you want to find a geometry is draw your Lewis structure, as we've discussed, and then you count how many electron groups you have around your central atom. Once you know how many electron groups you have around your central atom, you can then determine what we call the electron group geometry, and then from that determine the molecular geometry. Because knowing how many electron groups you have is what allows you to determine your geometry, it's really important that you know what constitutes an electron group. If you have a single bond between two atoms, that is one electron group. If you had a double bond between two atoms, that is also one electron group. If you have a triple bond between two atoms, that is also a single electron group. So we're not counting the number of bonds, we're counting the number of bonding groups that occur between two atoms. If you have an element with a lone pair, that lone pair is an electron group. And then, as I've said before, if you happen to have a single electron, it would also be an electron group. If you have two electron groups around your central atom, and the electron groups want to be as far away from each other as they can, then that means that they are going to be 180 degrees from each other, and they will have a linear geometry. So as you can see with carbon dioxide, the double bonds to each oxygen constitute one electron group, and there are two of them, so it's two electron groups total, and this is a linear molecule. If you have three electron groups around your central atom and none of them are lone pairs, then again, the electron groups are going to try to get as far away from each other as they possibly can. And that means that it's going to form an equilateral triangle with bond angles of 120 degrees. You can see that this is flat, right? They're all in the same plane as each other, and they're forming a triangular shape. So we call the name of this geometry trigonal for the triangular shape, and planar because all of the atoms are in the same plane as each other. Whenever you have three electron groups around your central atom, the electron group geometry is always trigonal planar. However, if one of those electron groups is a lone pair of electrons, then when you look at what it looks like as a molecule, the lone pair is essentially invisible, and so it goes away. And what you're left with is just the bottom part of what was originally a large equilateral triangle. And this geometry we call bent, because it's like you took a straight line and you bent it. When you have four electron groups around your central atom, the electron group geometry is always going to be tetrahedral. And if none of the electron groups are lone pair, then the molecular geometry is also tetrahedral. And here you're going to have a bond angle of 109.5. Now, one thing to keep in mind is the static image on the left here is showing that you have one hydrogen kind of sticking straight up, and then three of them are down below, and it makes this hydrogen at the top look special. But it isn't actually special, it's just an optical illusion. So if we look at the moving image on the right, I've started with the diagram roughly in the same position for CH4. But if we rotate it, okay, you can see that all of the hydrogens are the same as each other. So this view that I have here is actually the one that I prefer to use with tetrahedral geometries. And again, if you have 4 electron groups, you will have a tetrahedral electron group geometry. But if one of those electron groups is a lone pair, then your molecular geometry is called trigonal pyramidal. The idea here is that you have a short, squat pyramid, and it has a triangular base. So unlike trigonal planar, the atoms are not all in the same plane as each other. The central atom is sitting on top of this little pyramid. And so the bond angle is actually going to be less than 109.5. The reason for that is that lone pairs actually take up more room than bonds do, and they push all of the bonds down a little bit. And so it's like an umbrella that starts to collapse a little ways, and so the bond angle is going to be smaller. If you have a tetrahedral electron group geometry, but 2 of your 4 electron groups are lone pairs, then what you actually end up with is a bent molecular geometry. So this is the other way to arrive at a bent geometry. Water is probably the most important example of this, where there are 2 lone pairs on the oxygen, and then you have the 2 hydrogens, and together it forms a bent shape. And this is why I always write the Lewis structure of water as having a bent shape, just out of habit. When you have 5 electron groups around a central atom, again, the electron groups are going to spread apart from each other as much as they are able. And so the shape that you get here is what we call trigonal bipyramidal. The idea is you have your central atom, and then you have straight up and down from that what we call our axial positions. And those would be 180 total degrees apart from each other. But in the middle, between them, you have what we call the equatorial positions. And around the equator, you have 3 different electron groups, and they are spread out as much as they are able. So essentially, you're combining a line with the trigonal planar around the middle. So when you combine these two, it gives us our trigonal bipyramidal. The name, by the way, comes from the fact that you have the triangular middle, you would have a pyramid going upwards and a second pyramid pointing down. And so it's triangular and there are 2 pyramids. So one of the important things about trigonal bipyramidal is that you can tell the difference between the orientations. As I have it oriented now, I have the axial pointing up and down and the equatorial around the middle. If I rotated it, then you can see that it looks fundamentally different. You can distinguish between an equatorial position and an axial position when you move the molecule. Because there is a difference between the axial positions and the equatorial positions, it raises the question of which position would a lone pair be added to if one of the electron groups in the molecule is a lone pair. And for trigonal bipyramidal, the lone pair is always going to go on an equatorial position. The reason for that is if you have your lone pair on the equatorial position, it has 2 90-degree interactions and 2 120-degree interactions with other electron groups. But if you were to put it at an axial position, so that is 3 different interactions all at 90 degrees. And that's all very close. And it turns out that the lone pair would prefer to only have two 90-degree interactions and two others that are further away than to have three that are close up. So the electrons are never at the axial position, they are only ever at an equatorial position. The reason that this is called seesaw is because if you tip it over, it looks like a seesaw, aka a teeter-totter. If you have 5 electron groups, but 2 of them are lone pairs, then both of the lone pairs are going to position themselves in an equatorial spot. And so the molecule that's left over has both of the axial positions and one of the equatorial positions. And if you rotate this, it looks like the letter T, and so this is very cleverly named T-shaped. The final scenario for the electron group geometry of trigonal bipyramidal is if you have 3 lone pairs. And in this case, all 3 lone pairs are going to be positioned on the equator of the compound, and what's left is simply the linear component, the axial atoms that form a straight up and down line. And so the name of this molecular geometry is also linear. So this is the second way to achieve a linear geometry. So we have, in this case, xenon difluoride, and it has 3 lone pairs that you don't see on the xenon. All you see is the line it forms with the fluorines. The largest molecules that we talk about with Vsepr have 6 electron groups around the central atom. When that happens, we have what we call octahedral geometry. That's because if you connected all the outer atoms, they would form an octahedron. So if there are no lone pairs, the molecular geometry is also octahedral, and the bond angle between every single atom is 90 degrees. So you can think of it as having a linear, axial component with 4 around the equator. The only thing to keep in mind, though, is that unlike trigonal bipyramidal, there's no distinction between any of the atoms. So you can rotate it 90 degrees and it looks exactly the same as it did before. If you have 6 electron groups, and thus an octahedral electron group geometry, but one of your electron groups is a lone pair, that lone pair can go anywhere at once, because again, all of the positions are identical. Once it's on, though, what you end up with is a square base with one sticking up, and the one sticking up is different here. So if you look at the dynamic image on the right, you can see we have our square base and then one sticking up. And so the name of this geometry is square pyramidal because it's a pyramid with a square base. And then finally, if you have 6 electron groups, so you have an octahedral electron group geometry, but 2 of your electron groups are lone pairs, then this gives rise to the geometry that we call square planar. What happens is the first lone pair always gets to go wherever it wants, but the second lone pair is always going to try to be as far away from the first one as it can because they want to repel each other. And so it always goes on the opposite side of the molecule. And what you're left with is that square base from the pyramid that we saw earlier. Although I'm not enforcing any memorization in this class, it is in your best interest to memorize the information that I've presented on this table. The reason I say that is because you're going to be working with these molecules and shapes and drawing them a lot in this class, and the more of this information you have memorized, the easier it's going to make it for you as you work through the material. And that's how we determine the 3-dimensional shape of a molecule based on its Lewis structure.